No, English. Introduction about engineering.
Okay, so it's 7 o'clock right now. Let's get started. Good evening, everyone. My name is Emily Shawn. I'm a recent graduate of Wake Forest University and an incoming consultant at Oliver Wyman.
Hi everyone, I am Zirin Liu, a sophomore at Troy High School and president of Outreach Helping Hands.
So tonight we're very honored to welcome Dr. Yuqing Liu as our guest speaker on the topic of engineering. Dr. Liu currently serves as the Global Functional Manager of Stress and Vibration Engineering at Bechtel, one of the most respected engineering, construction, and project management companies in the world.
Dr. Liu has an impressive professional background. Dr. Liu studied at Tsinghua University for his undergraduate studies. He holds a PhD degree in mechanics, is a licensed professional engineer, and is a member of the ASME Code Committee. Beyond his professional achievements, Dr. Liu has contributed to over 40 paper publications and technical presentations, and holds an international patent as an inventor.
Thank you, Ziran. Now let's welcome Dr. Liu to share his fascinating work and insights into the world of engineering. Audience, feel free to leave your questions for Dr. Liu in the chat box during the presentation. Welcome, Dr. Liu.
Thank you. Thank you, Emily. Thank you, Stan. Um, Good evening. Welcome to this webinar. If you can see my screen, I'm going to talk about engineering can be fun. So um, um, this is my picture if you can see my video. Um, this is I want to start my presentation with a very respected lady, Katherine Johnson. She passed away during COVID. I share very similar education background with her. She worked for NASA. I also got my PhD and my bachelor degrees in the aerospace engineering background, and she spent most of her time in the mathematics. Actually, that's very similar to what I had when I choose engineer as my major. Actually, I didn't know much about aerospace engineering. I didn't know much about engineering at all. I just feel that it was cool. I saw that on the TV many times. Saw the launch the rocket, send people to the moon, send something into the aerospace. Looks cool. I feel like I want to design something for that. Um, that's something I would like to do for my career. But when I joined the school, just like as you can see, what she does, she's a NASA mathematician for the space program. So in my whole life, in when I was a study for my bachelor degrees, for my PhD degrees, even in the first probably 10 years of my career, I never even saw one single drawing of aerospace. All my first 20 years was spent on all the mathematics, equations, charts, figures, all of those. So Katherine Johnson was very famous in NASA and also in the aerospace engineering because many years ago when the computer was a new thing to us, like I should say 50, 60 years ago, at that time, even the NASA center And astronauts, they didn't trust the computer calculations. When the computer calculate, how should NASA send the people to the moon, and all the, you know, how much force required, how long it would take, how many cycles around the Earth it would take before launch on the moon. All of those were calculated by computer, and NASA did not have such a trust on computer at that time. So they asked Katherine Johnson to do a hand calculation to double check the calculation which was done by the computer. And she did that. And she was one of the few people that NASA could trust with such a task. And today, actually, with such advanced technology in the computer science, people would turn around. Today, if I do a hand calculation, some echoes in the background. If I do the hand calculation for a NASA program, I believe NASA would ask me to use a computer to verify my hand calculation, not the other way around. So, so that's how we start with all the engineering. So even I was surprised. I was a little bit disappointed in my first few years. Actually, eventually I liked it. Um, Once I get into it, and once I understand why do we need to do that, I feel that is important. And that's what I want to share with you. Uh, as an engineering, what do we do? And it could be fun, it could be challenge, and it is well paid. And we do also have a lot of innovations and AIs, machine learning that in our tradition engineering design. So, which I know most of our attendants in this webinar are high school students. 20 years ago, when I asked my friends, my coworkers who had high school kids that time, I asked, no, in which, what would be your kids' choice for career, for major in the college? Most of them answered me, they would let their kids go to medical school, be a doctor. That was a very typical answer 20 years ago, and they did. About 10 years ago, most of the parents would choose computer science for their kids and encourage them to go with the computer science, data science, and those even nowadays becomes AI. And very few people would choose engineer as their major in the college. Um, um, but engineer could be a well-paid career. Just want to say that. So this is a very recent study that we have. As you can see, which job is well paid, and when you start with the early career, as you can see, the petrochemical, which is most of the Houston people, in Houston, we have oil and gas, petrochemicals, petrochemical engineer. When they start the college, when they start the career after the college, usually they got an average salary around 90,000. And within 3 years of their career, the salary will easily reaches 120,000 a year. And when the reaches the middle career, such as after 10, 15 years, this average salary will reach 170,000. And that's a typical petrochemical. And if you compare that to some of the other computer science, now even though we all know that computer science can easily find a very good decent job and may get a really good paid in startup companies, and on average, computer science's career is not as good as the petrochemical, mining, marine, and that other engineering degrees. And even in the middle of the careers, even though they could still fall short when you compare that to the petrochemical, the marine, even nucleus, and the chemical engineers. Of course, we have some of the engineers they do for very short in the payment, but engineer overall is a good paid job. And the engineering has many, many majors. When many people think about engineering degrees, the first reaction was like electrical engineer, mechanical engineer, civil engineers, and maybe some of people would think of aerospace engineer. So actually, engineering majors has a lot more. In a typical major engineering project, we need a whole team of engineering by various engineering background. We have aerospace, agriculture, audios, and the biomedicals, and the chemical, geotech, marine, civil, computer, electrical, industrial, automotive, nanotechnology, mechanical, nuclear, petrochemical, material engineers, structural engineering engineers, architecture engineers, robotic engineer, control system engineer. Actually, there could be more. And now, when you're working for some, I have one of my college friend. He worked in aerospace and was studying acoustic. And later on, he found a job in California. He's now working for App, and he's designing the microphone for the iPhone. He's an audio engineer. So that no, a lot of things there. So I'm just briefly talking about a few quite interesting and exciting project that I personally designed, being part of that project. If about like 10, 15 years ago, when I first time started, after I started working as a project lead, Ivanpah solar power plant was the first job that I've been served as a lead. Ivanpah power plant actually is in California, um, about like an hour and a half driving from Las Vegas. So uh, this is it's a not a standard solar plant that you will see that use a PV panel. This is the plant we used 350,000 mirrors to focus the solar energy on the top of a tower. That tower is like 140 meters or 460 feet tall, and we focus all the solar energy on the top of that, and on the top there's a boiler. So during the daytime, once the mirrors focus the solar energy on the boiler is going to turn the water into steam. Then we let the steam coming down to the bottom. As you can see, at the bottom there's a traditional steam turbine, which turns the steam energy into the electricity. Overall, this can produce 392 megawatts clean renewable electricity, and this project cost the U.S. government 2.2 billions. Out of the 2.2, U.S. government paid roughly probably two, and I think probably Google paid the rest of them. And we took the land from public land, and it was abandoned military base. It was quite a challenge. Actually, in the beginning, we were designing for the 440 megawatts, and we already finished the design. And it was during the construction that we found around some corner there was a endangered desert turtle and living in there. We thought they were dead. And actually, when we started construction, we dig the ground. We found that there's still about 100 of them living in there. So we reported that to the government. We said, no, it was lucky that we found them. So in order to not to disturb their life, we decided to cut down our scope from 440 megawatts into a 392 megawatts in order to, so there's a center area we even though we designed for it, we during the construction we decided not to put the mirrors on that, so the turtle can live their continuous live their life in that area. So that could be one of the challenges that we have. So this job if you go to Netflix somewhere, there was a documentary called Planet of Humans, was back in 2019, which talked about the story of this project. And a few years ago, I was lucky to work on the NASA mobile launch. You probably heard that. And a few years ago, when Trump was the president, and he had the plans to resend the human back to the moon, and he planning to do that, finish that task within his term, but he didn't, and actually you can say has been delayed now. Even President Biden finished his term, we still have not done that yet. And that's a very interesting project. We're using a ground platform that launches a space launch system to the moon. So this is a mobile. The way we call it mobile is because you can locate it anywhere. It is running on the wheels, so we can move it to the location when we need to launch them, and then we can move it back to the garage and when it's done. And so we can keep reuse it, not like in the past, it's a one-time launch system. So nowadays you can see SpaceX and all of that, we try to reuse the launch systems in order to lower the cost. and this can send the astronauts and the heavy cargoes to the lunar surface as a part of the NASA's program. This design is 390 feet tall and 11.3 million pounds of steel. During the launching, there will be a highly blast temperature of more than 2,000 Fahrenheit degrees, and the blast force could be up to almost 9 million pound. And this job, I was also serving as a project lead on this job for the dynamic systems. We use liquid hydrogen, liquid oxygen, and to launch as the fuels for the rocket, and also we have to use the liquid liquid oxygen, liquid hydrogen, and we use the liquid nitrogen to cool down them. So at the bottom, you can see the liquid oxygen, liquid nitrogen, and liquid hydrogen are mixed down there. We use a very powerful pump to load them into the spaceship. And very high, and also during the spaceship launching, there will be only one side of the structure, and the system will see the launch blast for temperature. So the whole structure will behave like a banana, right? You only have one side has a high temperature, the other side is almost ambient, and so the structure is going to bend over when we launch the spaceship, and all of those we have to take that into the considerations. And that's also a very challenging project. Like I said, we've been way behind the schedule. We've been tripled. We have been more than tripled the original budget, and then many people asking me the question: if U.S. could send people to the moon back in 1950s, 1960s, why can't we just reuse the same technology and same drawing? Actually, now I got a chance to look at some of the old drawings that they used back 60 years ago. I would have to say that now, if we reuse those, um, there are chance that we will fail. I would say those drawings, those designs, they're not safe to today's standard. And not only that, many of the manufacturers. So when we're talking about design, we are not only just talking about we design the paper. We have to think about how we're going to fabricate them, how we're going to put them together, and what's the industry supply chains. Because we haven't sent people to the moon for almost 60 years, and many of the fabrication manufacturers have gone out of business. And even we try to use the same drawing as NASA had before, there's nobody in the market who can make such a product. So we have to design new stuff according to today's safety standards. And so that's another project I just did. And of course, in Houston, we have to deal with a lot of petrochemicals. This is one of the petrochemicals that I designed and finished the construction, and now it's running in Pennsylvania. It is when the project started, we call it Shell Franklin. The owner is Shell, one of the major oil company, and later on we changed the name to Pennsylvania Chemical, and it's located about 1 hour north of Pittsburgh. It's an ethylene cracker plant. They use the cheap natural gas from the local and make that and crack that and make that into the ethylene, and which is polyethylene is used various products like the common house good, like the plastic spoons that you're using, plastic bowls, anything plastic that in your house that you have the polyethylene stands behind them. So this job is a $14 billion project, and took us about, I would say, almost 8 years from the early design until we finished the construction and turn over, commission, start up, everything. Took us 8 years. And it can produce 1.6 million tons of polyethylene. And it is a mega job. You can see. So this is just one of the structures that we used. One challenge we had to use this job is instead of a stick build in Pittsburgh, we try to modularize. So most of the structures that you can see on this picture, actually they were not built in US. They were built in Mexico in order to lower the cost, because the labor cost in Mexico much cheaper than US. by a few times. So we let the fabricator in Mexico fabricated them. We loaded them on ship and shipped them through the Mississippi River and until they reached Pittsburgh. Then from there, we loaded them on the truck and sent them to the site. So that's another challenge. So we had roughly 250 modules and from 4 different module yards. We had 2 in Mexico, and we had 1 in Indonesia, and we had 1 in China at that time. So, and we have more than 1,600 pieces of equipment, more than 1 million feet of pipe, and more than 42,000 tons of structural steels we used, and more than 240,000 cubic yards of concrete overall used for this project. It's a huge one. And I was always proud that in my early career, I was involved in the nuclear. I started with that. And Wartsbar Unit 2 is located in Tennessee. And the Wartsbar Unit 1 was built by us, by my company Bechtel back in 1980s, I should say probably even 1960s or 70s. So, and because the owner run out of money, and also because the 3-mile nuclear plants located in Harrisburg in Pennsylvania had an industry incident, not a nuclear incident, it's an industry incident. So the leakage has nothing to do with nuclear radiation, but it's with other systems. But still, because it's located in Harrisburg and caused a lot of panic in US. And so at that time, US government decided to put a pause on all the nuclear constructions. So that's the reason the nuclear unit 2 was never finished at that time. So back in 2010, around 2010, because the new generation of the nuclears, we decided to continue with that project. It is a pressurized water reactor with more than 1,000 megawatts, huge one. So it's more like 3 or 4 times of the solar plants, that one part solar plants combined. It is the first nuclear reactor to come into the service in US in 21st century. So actually, if you look at the nuclear reactor designs, really there's nothing to worry about the nuclear radiations. We have a triple protection for that. So not only the nuclear radiate, the materials, the water will never leak out. They will be encircled in a huge concrete dome. And people will never get in there, and anything leaked in there will never get out. And so the unit uses nuclear fuel rods to heat the water, and that water comes to heat another water. So there's a heat exchanger between the nuclear building and the non-nuclear buildings. So the water that contacted the nuclear fuel, which has the radiations, will never come out of the nuclear reactors. Instead, they will be used to interchange the heat with the water outside. Then we use the water outside to turn that into the steam and drive a traditional steam turbine to generate the carbon-free electricities. So nuclear is also a very green energy, and once you start it, you will never need to worry about carbon capture release or anything like that. And so this job cost us $4.4 billion to finish. And so um, nowadays, actually, my company restarted many of the nuclears. We have another nuclear job in North Dakota called Natrium. It's a very small one. It's designed. We Bechtel worked with Microsoft, Bill Gates. Bill Gates has another company. I forgot the name. Called Aero Power or something like that. So he founded that and nuclear facility. So we work with him. We build a small plant in North Dakota to demonstrate the capacity of his nuclear designs. And we are also now working in Poland to build the nuclear plants there, because of course, because the war between Russia and Ukraine, of the East Europe European, they don't trust the electricity, which in the past they've been taking that from Russia, and now they want to have their own independent energy supplies. So we are also helping them with that. So nuclear is one of the futures. So LNGs, my company actually is probably the most famous company in the world building the LNGs. My company built up 35% of the nuclear capacity of the world, and also built up 37% of the LNG production in the world. So LNG is also a clean energy. So because once you burn the LNG, all the byproducts you will get is just the water. Okay, water and the carbon, of course, some carbon oxygens, and LNG becomes so important also right now, also because the war between Russia and Ukraine. Before Russia invaded Ukraine, all German, France, Poland, and all of those European companies, I mean, not European countries, they import natural gas from Russia for their daily use and for their industry use and also for the commercial use. So after the invasion happened, they decided to cut that from Russia, and then no, European, they don't have their own natural gas, they don't have their own oils, so they have to take it from somewhere. So at that time, U.S. government decided to help our allies in Europe. So we started making a lot of LNG export facilities in Texas and Corpus Christi and Sabine Pass, Port Arthur in Louisiana, a lot of them. Now we're building Rio Grande, and we're also building Mexico Pacific, many of them. So in order to make the natural gas into a liquid natural gas, we have to cool them down to a cryogenic temperature, roughly negative 230 Fahrenheit. And so that way we can the natural gas becomes a liquid, and then we can load them into the ship. So a typical LNG plant takes more than 1,000 arcs. This kind of a project takes us to $23 billion to finish. It can produce 33 millions of tons of LNG per year. And a project like this also takes a lot of civil engineers, mechanical engineers, petrochemical engineers, effort, electrical engineers effort, marine engineers effort as a team to make this job happen. As you can see, this is how in order to load them into the ship, it has to get into the negative 162 Celsius. Then we turn that into a liquid from the natural gas, from the gas into a liquid. Then we put them in the LNG tanks before we, that's an energy tank, before we eventually load them into the ship. And the ship will be sent to France and Germany, those European countries, and to provide the LNG to them. And in the past few years, you probably heard a lot of news about the semiconduct. It's also because in the past, Taiwan probably the biggest supplier of the chips, right? You heard of the news a lot. Taiwan is the biggest manufacturer and supplier of the chips of the whole world. And of course, because recently, there are some people, it's not just thinking about it. It becomes true that they worry about China may invade Taiwan and using a force and take over Taiwan, and in that way, all the chips production will be falling into Chinese government's control. And so when people have such concerns, they decide to make those plants in US and in Germany. So we are working with Intel. We took about $20 billion from government. President Biden approved that money for us to use, takes from the taxpayers' money. And so we're building one Intel semiconductor plants in Ohio. It is one of Intel's global factory network to fabricate the chips and create more than 10,000 jobs at the local place. We're also working with the government to make a plant, such a plant in Germany, also one additional one in New Mexico. All of those just to diversify the suppliers of the chips, not just in case the Taiwan was taken, and so we still can have the chip supplies. And so after talking about all of those the exciting projects, I want to talk a little bit about the um, uh, of the mistakes. So engineers mistakes happen a lot of times. My personally has experienced a few of them, and but here I want to just talk about a couple of them. The one on the left, that's you probably saw that on the news recently. Baltimore Bridge collapsed by one of the cargo loading ship, and at least lost about 400 million, at least about that, and 6 people was found dead. And I'm not talking about who made such a mistake, and just talking about the design, engineering design. That bridge was never even designed correctly if today, based on today's standards. So if we had a chance to redesign the bridge, definitely we would not even go with such a design. That design was very weak, and it relies on the operator of the ships to be 100% correct. They did not design for any margin just in case people made a mistake. That's not today, according to today's standards. Today's standards we always design for predictable mistakes. So if you know people may have a chance that operate the ship and hit your bridge, that you would have to design for that. So that's a mistake. And some of the mistake in petrochemical could be really, really costly. Like the one on the right side, bhopal gas leakage in 1984 in India. Immediately, it leaked around midnight, and it's close to a very, in India, the population is so dense, and close to a small town, actually a small town in India, but enough people living in there. So when the leakage occurred in the midnight, about 4,000 people, I should say, 3,800 people was killed immediately, even before they being alerted, and more than 500,000 people injured. And it's just because of leakage in one of the petrochemical plant. So those mistakes could be really, really costly. Not to mention many other mistakes I have personally experienced. Um, and so that is a one of the reasons that as an engineer we have to be well educated, and we have to continuously educate ourselves. And based on the lessons learned, based on the other people's mistake, based on all the new things going on, all the new technologies, and even every time when we receive an innovative technologies, we have to carefully review what would be the consequence if something went wrong. So that's one other thing. So here, of course, Fukushima. I said many years ago I designed a water spot unit 2, and that was the last nuclear job that I designed. Then I lost my job. Then I moved to Houston to start working on the petrochemical and NASA project. Why? Why did I did such a good job on that water spot unit 2? Why did I lost my job? It's because of Fukushima. Because the Japanese made many mistakes in their Fukushima plants, and so when they're being hit by a tsunami after earthquake, their nuclear plants failed. We today when I reviewed that report, there were many things we could have done to avoid such a failures. I'm not going to go through all the details, but here's just a picture. So after the Fukushima nuclear plants failed, and the whole world just couldn't trust the nuclear energy anymore. So instead of building more nuclear plants, people in Taiwan, in Germany, in US decide to decommission their nuclear plants. So with that, my company decided to close the whole nuclear business, which impacted more than 4,000 people's job. So yeah, so that was one of them. So you can see, even the mistake was not made by me, made by my company. People we will also get impacted because made such an impact, huge impact on people's life, and nobody trusts nuclear at that time. Now after almost 10 years, people we are moving back to nuclear again, and I'm really hopeful not we will not experience such a mistake again. So had enough about all of the projects we have, and now I know for the new generations, people wants to say, what's new in the traditional engineering industry. We do have a lot of innovations here. I just list a few. Actually, there are more. One of the uh, my personally likes the innovation about the robotics for inspection and maintenance. As you can see in the nuclear, in the petrochemical, in the NASA, there are many of the, I would say, the structures, buildings that it's hard for us to send people in there, like nuclear reactor buildings, like the one that Fukushima had failed. During the daily day in, day out operating, there's no way we could send a human into the structure to do the inspections. So we had to, so nowadays with robotics for the inspection and maintenance, that makes our life much easier. We can use the robotic things into the areas that we cannot send the people over. And also not only nuclear, we're talking about the chemical reactors as well in the petrochemical plants, and also some of the offshore projects. In the offshore, you can people has a limit how deep you can dive into the ocean, but robotics does not. They can dive in much deeper in the ocean to do the inspection and maintenance there. So robotics has been a major innovation in the traditional engineering field for that. Not only that, drones is another one for working in the dangerous and remote areas. So in the past, when we, for even for example, you can see for the windmills, in order to do the inspections, traditional way was send people out there and have them take a look, right? And that was a really dangerous position. And we have seen a few stories about when the people was doing the inspection on top of the windmills, and it was set on fires, and people could not get it done, and they dead. And if now we more often we send drones up there to do the inspection in the dangerous areas which we could not send the people over. And we also send the drones even for the deliver. I had one of the story that during a hurricane season, hurricane hits Texas quite often, a few times a year. During the hurricane seasons, we had to um, 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 put the team in a safe place. So one of the offshore drilling platform had no people there, but they had to shut down one of the valve. They forgot. So if the hurricane hit that platform with the valve open, they could cause $1 billion lost. So we cannot send people back. So and that platform is about like 30 miles from the shore. So we decided to send a drone, and very few companies has such a powerful drone that can survive in the hurricane and fly 30 miles for such a task. And luckily we found one. And they have a very strong drones that can fly 30 miles in the hurricane season, and successfully shut down the valve and safely return back to the shore. And that was amazing. That was amazing. Yeah. So that was one of the innovations that we are having as well. So not only that, today's the AI has been widely used in the energy industries, such as a smart grid. And you probably have heard a couple years ago, Texas has experienced a major power failure because the power grid was also outdated. And so nowadays we have implemented the smart grid, which can identify in which areas you need more power than the others, so they can automatically switch the voltage to shift the more electricity to the areas that they need them, and and also to keep a balance between all the renewables. Some of the renewables energies have their disadvantage, such as the solar plant. You cannot produce electricity at night, and so we rely on the AI to learn the smart grid to. So during the night, we know that some areas will have less supplies where people there, once they turn on the air conditioning, they need more electricity. So we could transmit more energies from other areas to help them out. So not only that, so actually as an engineer, we not just do our daily jobs. We have many societies. The mechanical, we have ASME. Electrical, we have IEE. Chemical engineer, we have AICHE. And structural engineers, we have ASCE, and many more. And we almost every month or every few months, we have a major conference in the US or internationally. We have exhibitions. We have the fabrication and the suppliers to show us the new products. And we also do the engineering without board to help other countries in Africa, in Asia, whose engineering education was much poorer than ours, and they don't have good engineers, don't even have actually good equipment, tools to do the calculations. So we volunteered to help them to do the engineer job for them, just to help them to build their infrastructures, bridges, road, wells, to improve their life. We do all of those based on volunteer. We don't charge them. We just help them. And we also now we run marathons. We have a lot of other activities as an engineer society. This is one of them. We just recently had in Houston, the Houston Chevron Marathon. We hold that every year, and so engineer could be a lot of fun than you originally thought. And then I originally thought when I started my first career, I was thought, no, this is so boring, just so many equations. Then after 18 years working in this company, also I spent almost 8 years, 9 years getting my PhD degree and bachelor degrees. I spent almost 25, 27 years in this engineering field. I started, I learned a lot. I started like the ideas, like what I'm doing right now. And
不是
I
说
also
介绍啥玩意儿，这咋都说英语？你变大是这样子啊，这样子。Amy 是谁？
okay.
不是 Amy，读 Engineer Society。
Somebody needs to mute himself, mute herself. Yeah. So I also been serving as a code committee in the ASME, and not only help the ASME. Nowadays ASME and all of those American-based engineering society has taken over other countries. Like if you go to Canada, if you go to Mexico, if we go to many other countries in Africa, in Australia, in Africa, they don't have their government don't have their own engineering societies. They heavily relies on American societies to help them out. So the government would just say, okay, just use the ASME standards or use the ASCE standards. All of the A here means American. So original purpose was just to set up the societies for the American engineers, but now half of the world is using it. So we also hold international conference to help them also provide international educations, trainings to make their engineers familiar with our ASME, ASC standards to do their job, do their designs. So it could be quite fun, And I think, yeah, I think now I can. I'm done with my presentation. If I'm ready for if you have some questions.
Well, thank you so much, Dr. Liu, for the insightful and fascinating presentation. I especially learned a lot when you shared about the exciting projects you were involved in. I think these projects are truly impressive and have a huge impact on our daily lives.
Thank you so much, Dr. Liu, for your insights. After your presentation, I'm sure we all have a lot of questions for you. I'll start with one. What was the most challenging aspect of being in engineering during your journey?
That's a very good question. The biggest challenge is how to find a balance between the quality, cost, and the schedule. I'm still facing such a challenge on every job. So give you an example. Today, if you go into a class, you need to take an exam. You need to finish 10 questions in an hour. And you could, like when I was high school, I would finish 10 questions in 40 minutes, then I can go outside to play video games. And then I may turn out to find only 6 out of the 10 questions I finished, I made them correct. And the other 4, I made mistakes. So I only got a 60 out of 100. So even though I finished within my budget, I finished in my time, I didn't really have a good quality in my work. So, or I could do it the other way. I could be very careful about my calculations, about the examinations. I can double check my work I finish each question in 10 minutes. Then when the exam, 1 hour exam is done, I only finished 6 out of the 10 questions. I still only got a 60 out of the 100 because even though I finished within my hour, even though I finished within high quality, I finished in my budget, I didn't meet my schedule. I only finished 6 out of the 10 questions. Or I can do another way. I can send 2 people if the teacher allows me. I can send 2 people to the classroom. Let each one of them finish 5 questions and let them cross-check each other to make sure the high qualities and all of that, right? So end of the day, I got a 100. I have a high qualities. I finish all 10 questions. But guess what? I didn't meet my cost. If my budget is only 1 person 1 hour, and in this task I spend 2 person 1 hour, I didn't get paid enough for that work. So as a company, I have to run a business, I have to make money, make profit. So if I do things like that, I will lose money, I will bankrupt. So all of the major jobs that I showed you here, when you can see every job, I try to give you an idea. This job costs us $20 billion. This job costs us $23 billion. This nuclear job is $4.4 billion. This job is $14 billion. As a engineering manager, that's something in my daily life. Every day when I make decisions, not only I have to consider the quality of my products, and I have to consider the schedule that I need to finish. Also, I need to consider the cost. I do have a fixed cost for such a project. Yeah. So I'm still facing that challenge, but that's a very good question. Thanks.
Thank you. I also have a question. You mentioned how costly and terrible mistakes can be in engineering, and I'm wondering in your daily life work, when you work in projects, how do engineers collaborate to try to avoid mistakes? Are there any other parties involved to help you with that?
Yes. So first, when we start any projects like this, so we try to follow the standards. So all of the societies in American SC, SMEs, we set up some standards, which is based on the previous experience and lessons learned. So we try to design per those standards. And if we could not, now I would say if I have 100 designs, maybe 95 of them they could meet. There are always a few designs that we cannot, or we try to use some of the innovative ideas which was never discussed or covered in those society standards. Then here we need to get involved with some outside consulting companies to do some testings. Like for the nucleus, we sometimes engage with Japanese companies to do the shaking bed. We put our milli-scale structures on the shaking bed to see how long they can survive in a major earthquake event. And we also do a third-party validations. So we don't just rely on everything on the calculations, and we also try to say what if our calculation is wrong, and how much additional margin do we have. So for those like a nuclear appliance, we always have additional safety margins. So just in case the design was wrong, something went wrong, something leaked out, we have the second round of protection. And what happens if the second round of protection also failed? We have the third round of the protection to reduce the overall disaster. Yeah. That's good.
Got it. Thank you.
Mm.
Now let's take a look at the question the audiences have for Dr. Liu. And for audience, you can also unmute yourself to ask questions.
Jonathan had a question. How does AI impact engineering? How do engineering major students embrace AI?
That's a good question. And that should be your question in your mind if you decide to choose engineering as your major in college. And AI has, from what I can see, it has a major impact on almost everything we see today. Not only in the computer science, data science, also the traditional way we do the engineering. So like I'm working on one of the AI project right now, with a few other PhDs. We try to, in the past, we used to have a lot of people do the calculations, right? And we're trying to using a machine learning and to optimize the design. We pick up the experience from those experienced engineers and to try to understand what's the logic in their mind in order to make a decision choice. And then we build that logic using AI and machine learning, and to build a database that can simulate the way that a traditional engineer think and to make decisions. And so they can be a better engineer than the people that I have. So that's the one thing I'm working on right now. Yeah.
Thank you. There's another question from Tracy. The question is, what advantages and disadvantages, challenges do women engineers have?
Oh, that's a very good question. So it is very challenging, I have to say. I held a lot of college house, and I try to mentor them. I try to teach them. I would say most of the guys survived and they stay with me. And most of the girls, women in engineer, they even though they were happy working with me, they overall were not that happy with engineering. So we had a survey actually in Houston's engineering. We found 80% of the ladies who got the engineering degrees out of college, they choose to be engineer as their career. No, another 20%, even they finished engineering degree, they choose something else. So 80% of the girls finish the engineering degrees, they choose to be an engineer. But if we track them after another 15 years, those 80% becomes 20% after 15 years. So that means majority of them, after 10, 15 years being an engineer, they decide to quit their job and to do something else. There are many reasons for that. There are family reasons. No, there are tons of other reasons, and there could be they feel so boring or something like that. So it is quite challenging. So that's the reason we as a manager, I also do my best to keep my resource, especially the women in engineers, the experienced women in engineers. I make sure they are happy with their assignment. I make sure they could find a good balance between their life and the work. So I have to say, whenever there's a chance, I always um, help them not to work too much overtime, not to be overloaded with the life. I care about if they're happy with their assignment. If they don't want to go to the job site in Florida for the NASA job, I would not force them to go. If they don't like go to uh, Georgia for the nuclear war goal, I'm not going to force them to go. Whatever I can do within my power, within my authority, that can make them happy, that can continue, can help them to continue their career as an engineer, I would help them out in that. I do see a lot of challenges from them. They be happy working with me, give me a lot of honest feedback about what they like, what they don't like in the work, and I always try to do my best to help them out. But it has been overall has been a very challenge for women in engineer. Yeah.
Cece asked, where did you do your first internship and what were some things you learned and challenges you faced?
That's a good question. Yes, my first internship was actually it was in China, was in one of the government controlled institute, because like I said, I come from the aerospace background, so it was for the space program. So uh, that helped me. So actually, when I come to US, when I try to find my dream job in Lockheed Martin, in General Dynamics, and they look at my face and say, "No, you are Chinese. We don't need you here." And of course, they didn't trust me. I was a Chinese citizen, so I didn't find a good internship in US. But my first internship in China was a very really a good experience for me. Mhm.
I have another question. How do high school students prepare for college if they want to take engineering as their major?
Oh yes. So if you want to be an engineer as a major, I would definitely encourage you to take more AP class as a STEM, and make sure you understand you have a good you really like the mathematics. Even though many of the design, like I said, when I was designing, I know my first 10 years actually, maybe even 15 years, I never even see one single drawing of a spaceship. all my work was done on mathematically, and which is true for most of the, doesn't matter the mechanical engineer, aerospace engineer, or structural engineer, or marine engineer, or even nanotech engineers. Most of the engineering are based on mathematics, based on equations, which I hate. In my first few years as an engineer student, I really hated that. Later on, when I get into my work, I published so many papers, I got my patent approved. I started to realize actually that is the foundation of the engineering work, of the engineering design.
Ming asked the question, what is the best thing as you be an engineer and scientist?
Ah, good. Yes, I always say I don't enjoy everything in my work. There are boring part, there are fun part. To me, the fun part is when I come to my age, I start looking at my next generation. Um, I started planning for my retirement and started thinking who can replace me. Technical wise, who is strong enough. So I started. I've been a mentor for many people. I mentored more than 10 people for their careers, and I started seeing what's the strongest, what's the weakest in the qualifications, and to help them build up them for the future. So I do set up a plans for them in the next year. What do you need to do in the next 5 years? Where do I see you going into in the next 10 years? Or where do I see you going into? So and I make sure they follow my path so I can build the team. And after 10 years, if I decide to retire, I still have a good team with me. My company has survived in this industry 130 years. So it is a private company. So the first generation of Bechtel passed to the second generation of Bechtel family now become the fourth generation of Bechtel family. So that's the way that we in this company, and that how we pass our knowledge, how we pass our leadership to the next generation. And that's the part I really enjoy, and that's why I'm so encouraged. I'm so excited to talk to the high school and even college students like you. I want to see some of you decide to choose engineer as your major, and after you graduate from college you choose engineer as your career, and you don't have to choose back to as your employee. There are many other great companies, engineering companies there. You can choose working from them, and maybe in one of those engineering society event like I passed here, and we may come across each other. You know, so actually I did actually. A few years ago, when I was in one of the event, I came across a lady, and she told me she was working for NASA, and she said she attended one of my webinar, and in order to choose aerospace engineer as her major, and now at that time she graduated. She just graduated and was hired by NASA as a college help. And she attended the event, and she attended my seminar and my presentation in that event, and came to me and said, "Oh, I still remember you." I was so happy.
We've got another question. What personality traits do you think are necessary for a good engineer?
Oh yes, you have to care of what you're doing. I do see many engineers just came here for a job, for a salary. Like I said, engineer could be a well-paid jobs. They they jump around. They come here working for my company a year. They don't really care about what they're doing. They leave the work with a lot of mistakes, and they work for another company for another year. Just keep jumping, chasing for a higher title, higher salaries, and end of the day, after 5 years, they come back. He try to contact me and try to come back, and I interviewed him again. I realized in the technical wise, he didn't improve much, and because he only cares about a bigger title, a higher salaries. He never really cares about what he was doing. So as a good engineer, you really have to care. Doesn't matter whether you design. You may design an iPhone, or you may design a electrical vehicle, or you may design an energy plant. Doesn't matter you're doing, you have to care what are you doing. You have to remember that as an engineer, oftentimes we put our signature, our name on the design, and um, I just want to quickly share a lesson learned many years ago. One of the nuclear plants that an engineer made a mistake. The nuclear reactor supposed to, during the operating, has a thermal movements to the north 2 inches, and during his design, he considered as a south 2 inches. So he designed it in totally opposite direction, which causes that piping to broken and causes the nuclear coolant to leak out. And we found out, government found out, and put him behind the bar, put him in the jail. And because he put his name, his P stamp on the drawing, and he didn't really care. So yeah.
There's another question. Why should a high school student decide to major in engineering or science?
Major in engineering and science. Yes. I would definitely encourage you to consider, as I was considering, it is a well-paid job, and the U.S. need engineers. As I can see in my team in Houston, less than 10% of the employees in my group were born in US. More than 90%, they were coming from China, India, Korea, Malaysia, Indonesia, from Romania, from Poland, and very few, less than 10%, were born in US. So US kids don't want to be an engineer. They want to do cool stuff. They want to be a computer science, data science, want to be a lawyer, want to be a doctor, want to be a salesman, and less people in the high school, many people thought, no, engineer, no, just nerdy, and not get well paid. It's more like your plumbing guy or like HVAC guy. No, engineer could be a really well paid job, and could be a cool job, and could be a fun job. I would definitely want to see uh, more kids in the next generation to consider as an engineer as their job. So we don't have to rely on people from China, from India to come to US and to take over the engineering jobs. Our kids could be better than them.
We have a question from Mina. For a teenage girl who loves engineering but not super good at math or handy at mechanical works, do you have any advice?
Oh yes. So even though mathematics is a foundation of the engineering, in the engineering world, we do have some. No, it's not an unusual thing to say some girls not so super good in the mathematics. I do have a lot of girls, and they could also do many other things. They can do supply chains. Now, even though we finished the design, we did the engineering, we did the calculations, we still have to make the products happen. And in that way, we have to talk to the supply chains to see who can fabricate them, and when can they ship them to the site by the time we need them. And that requires a lot of skills, more than just the mathematics. Requires a lot of communications, and the time management skills, which are the in general, girls are better than boys in those, in the management skills. So in my company, we do say almost half of our senior management are ladies, are women, and very good in the leadership, in the communications, in the time management, multitasking, management skills. They could be way better than the guys in those fields. Yeah.
Thank you. I think that's all the questions we have for now. Let's see if we have any more questions. I think that's all. So once again, Dr. Liu, we really appreciate your time and insightful sharing about engineering tonight. I'm sure we all have gained very valuable knowledge and inspiration from your presentation. And thank you for taking the time to be here with us and sharing your expertise. We're all very grateful. Thank you.
Thank you very much,
Thanks.
Dr. Liu.
Thanks everybody for attending it.
Thank you.
All right.
Plastic is not wasted.